we'll see how to implement generative adversarial networks, or GANs, in PyTorch. GANs have been shown to be very effective in synthesizing new data examples that resemble a particular data set. And the high-level idea is to train a generative neural network, which takes in as input a random noise vector and then produces photorealistic data. So this has been a major success story in the last several years in deep learning research. But that's not the end of what we can do with GANs. So for example, we would like to have control over what is generated. For example, if you want to synthesize images of, say, dogs, then one could train a GAN which can synthesize dog images, but then as the user, one might want to have additional control over what is being generated. For example, you could want to say that I want a golden retriever with particular fur color with of a given size. So the type of the breed of dog, the color, and say the age of the dog could be auxiliary input variables to the generative model. And in that case, how do we train a network to obey these auxiliary inputs? So that is achieved by what's called conditional GANs. So we'll explore that in today's notebook. For this demo, we'll just use the standard MNIST dataset, which is, as we've seen before, a bunch of handwritten digit images of 0 through 9. So that will be sort of the class label that will feed as input to our generative model, and our output will be images of that particular class label. So let's see how to do that, and we'll start as usual with some basic imports, which we usually do. So as we said, we'll use the MNIST dataset. So we've seen how to load that several times in the past before. So having set up, having downloaded the data, we'll now see how to set up the model. So the input, as we discussed, will be not just the noise vector. The input of the generator will be not just a noise vector, but also class label. So this is can be used. This can be encoded in different ways. So we'll just use a one-hot encoding to represent this, and so a function to visualize how intermediate inputs, intermediate samples generated by the generator, how they look like. Okay, so the meat of the architecture are consists of the generator and the discriminator. So in this exercise, we'll just use simple dense multilinear perceptrons for both generator and discriminator. It's fairly standard. So generator, it's the opposite of a standard discriminator type architecture. We start with a small number of features, and then you end up with a larger number of features. So it's in some sense expansive. As you can see, the number of neurons in each layer increases, right? The only difference between vanilla GANs and conditional GANs is that vanilla GANs take in noise input, but conditional GANs also take in through the class label. So in this case, we have 10 classes. Therefore, we'll add a sort of indicator vector of size 10 along with the input. The rest is the same. In this case, we'll use leaky relu along with batch norm for our hidden units. So fairly standard. Since we are generating black and white images, you can just think of squishing the output between 0 and 1, and that's done using a GAN. Okay. So that's actually fairly standard. And similarly, the discriminator is also looks standard. So we'll use the multi-layer perceptron for discriminator. Notice again here that's the slight difference. So in a regular discriminator, in the vanilla GAN, we'll just take in an input image, right? And then check whether it is real or fake, right? So input is an image and output is a scalar. Right? Here it's the same thing, except that we'll also taken as input the class label, right? So what the discriminator is actually evaluating is not just the quality of the image generated by the generator, but also whether it belongs to the correct class or not. Right? So it's a bit more information than what a standard discriminator does in a vanilla GAN. But that's about it. I mean, there's only two differences. The other differences in the data, of course. In a regular vanilla GAN, you just need examples, like unlabeled data samples. But here you need class labels as well, because the input to the discriminator requires class labels for the real data points too. So that's about it. This is the architecture. I'll just set it up. And as usual, we know how to set up the data loader, which we've done before. Cool. It's about it. For more complex architectures, we won't use multi-layer perceptrons, but rather deep convolutional generators and also deep convolutional discriminators, but that's a story for a different day. Okay, so training is training of the GAN, both the discriminator and the generator is exactly the same as what we would do in vanilla GANs. It's cross-entropy loss because we are detecting whether sample is real or fake. Optimization done using Adam. One point to note here is that we are training two networks, so it's common to use two time scales, right? So you can train the discriminator for a certain number of epochs and a certain number of steps, and the generator for a larger or smaller number of steps, right? Typically, the discriminator is trained more number of steps than the generator, right? So for this particular example, we just keep both the rates the same, but this parameter critic basically updates the discriminator some number of times, and the generator only 1/k of those times. Right, so that's basically it. For this particular architecture, we'll use a 100-dimensional noise vector. Okay, so that's about it. Make sure to label your label your samples in each mini batch, right? So real data points are given the label 1, and fake data points are given the label 0. If you want, you can save images to visualize how they're doing in between. That's about it. So this we have again seen before. We just generate a random Gaussian noise vector, feed that as input to generator. We'll also feed in the class label, which is the only difference from the vanilla GAN. Compute the generated images, associate the same class label to the generated output, and pass it to the discriminator. That's about it. Right? So there are, if you remember our treatment of vanilla GANs, we have two loss terms, right? So we have the a real data points and the fake data points. So therefore, we'll have two loss terms that we use to train our discriminator. Similarly, we'll use that loss to also train the generator every k number of steps. Yep, that's about it. This also saves intermediate images, occasionally. Right? You can track how things are doing. This is being run on GPU. GANs require, again, since there are two networks, very quickly we run into the issue of training time. So expect to spend a good amount of time training even simple GAN models such as this one. This particular example should take about 10 to 12 minutes on Google Colab. So we are about halfway through the training, and as you can see here, we can track how the images look like in intermediate steps, and already we are beginning to see interesting structures. So each row is a particular class label, and different columns are different instantiations of the noise vector fed through the generator. And they're not quite all the way there yet, but one can already see the digits beginning to get formed by this time. Okay, so that took about 11 minutes. As you can see, the discriminator and the generator loss don't quite go to zero. It's common. This is very common in GANs, because GANs, it's like a two-player game that you play. So what you really will converge at is not like a global minimum for both discriminator and generator loss, but rather a saddle point, some point in the surface which is reasonable for both discriminator and generator. So it's not uncommon to see this kind of loss curve. Okay, so let's see how we do. So this is a bunch of images that you get, and as you can see, we do reasonably well already. You can see that different rows are different class labels, columns are different instantiations of the generator output, different noise vectors. We can see that class labels are respected. So the conditional variable is actually influencing what you see. So if you put in a conditional variable as a 4, you actually see only 4 images and not say 1 or 2. So that is respected. Also interesting to see diversity in the output space. So it's not like we simply get like a vertical one each time. We get ones of different thickness, orientation, and so on. So that's nice to see. This is showing that the GAN model is avoiding mode collapse. Things could be better. Let's see artifacts. So 5 could perhaps look like a 6. 3 and 8 are always hard to distinguish. So the artifacts persist. These can be changed, or this can be mitigated to some extent by changing the loss function. Instead of using vanilla GANs, we can use other types of loss functions, like Wasserstein loss and so on. That's about it. This is how conditional GANs work, and feel free to adapt this to your own problem instance.